Hi y'all, so in this supplemental video, we're going to cover the antiderivatives of e to some number times x, sine of some number times x, and cosine of some number times x. The only caveat is this number k cannot be 0. So let's begin. And the trick here is we're really going to be using u substitution to help us out. So I'm going to start off with the big spoiler. The spoiler is, for these types of integrals, like e to the kx dx, the antiderivative is actually going to be 1 over k e to the kx plus c. So let's actually see where this antiderivative comes from. So again, this was our spoiler. So if we start off with this integral, say e to the kx, now, the integrals that we actually know from our basic antiderivatives would just be an exponential by itself, like an e to the x, whose antiderivative is very lovely, just e to the x. But for us, what's kind of throwing a little, curveball is this k that's sitting here, where k could be something like -2, it could be a 5, something like that. Well, for us, since we don't exactly know how to anti-differentiate e to the kx, it's not one of our basic antiderivatives, we can actually use u substitution here to help us. So for example, if we let u equal that kx term, our derivative du dx just gives us k, since the derivative of kx is just k with respect to x, and then doing our standard stuff for u substitution, we need to solve for dx in terms of the new variable du, and we would get that, well, du is equal to k dx, and then dividing both sides by k, we find that du over k is equal to dx. So these are the things that we can substitute then into our original integral. So original integral e to the kx now becomes an e to the u, since we let u equal kx. And then we get to substitute in for dx, which we found dx is equal to du over k. So what this integral really looks like for us then is, remember, k is any non-zero number. We can bring that 1 over k out in front, and now we're just looking at the antiderivative of e to the u du. And what's nice about this is we know how to anti-differentiate an e to the u. That just gives us back an e to the u. And then we have our friend plus c. And the last thing we get to do here is, well, we don't want our antiderivative in terms of u. We need that antiderivative in terms of the original variable, which in this case is x. So we go back to our substitution, and we can just swap in kx anywhere we have a u in that antiderivative. So at the end of the day, our antiderivative here is 1 over k times e to the kx plus c. So that is where this relationship comes from. And to kind of take this a little further, what this immediately means for us then is if we have something like e to the minus, say, 13x dx. We know that this antiderivative, we just take the k, which in this case is minus 13. And it's just equal to 1 over k, again, minus 13 in this case, e to the minus 13 times x plus c. And the same method will actually work for sine of kx and cosine of kx. So without going through those examples, you would use u substitution still to do those examples as well. But if we go through with the antiderivative of sine of kx, which we will in 1 second, we can find as a spoiler, the antiderivative of sine of kx is a minus coming from the antiderivative of sine itself, but a 1 over k times cosine of kx. And of course, plus c. So that is our spoiler here, and let's just go through and see where this comes from. And the process will feel very similar to what we just did for e to the kx. So starting off with our original integral, sine of kx. We know what the antiderivative of just sine of x is, not a sine of kx. So we get to use u substitution. We let u equal kx, which means the derivative with respect to x of kx is just k. And we can solve again for the dx in terms of du. And shuffling things around, we will find once again that dx is equal to du over k. So plugging all of that into our integral, we get that we have the integral now of sine of u. And then we have a times du for swapping the gx for a du, which is a du over k. So the antiderivative then, well, I guess first we can pull that 1 over k out in front of the integral. So we're just looking at the integral now of sine of u du. And again, k is could be any number here except for 0. And the 0 case should throw a few red flags, because if k is equal to 0, we get a 1 over 0 right there in that term out in front. So k can't be 0 for these types of problems. And now just moseying on along with this integral, we know the antiderivative of sine is a cosine. So it's looking like 1 over k times minus cosine of u. And then, of course, plus our integration constant c. And again, the last thing we get to do here is really anywhere we see a u, we need to go back in terms of our original integration variable, which is x. And we can do so right through our u substitution. So anywhere there is a u, we replace that with a kx in our final antiderivative. So that just gives us a minus 1 over k times cosine of k times x. And of course, plus c. And that is our final antiderivative in this case. So just so we're on the same page, what this means is if we had something along the lines of sine of, say, 13x dx, the antiderivative would be a minus 1 over 13 times the cosine of 13x plus c. Now the same thing will work for cosine. So for example, I'm not going to go through this example, but you could do this the same exact way with u substitution. So if we have the integral of cosine of kx, where k again is any number except for 0, the antiderivative here is just going to give us a 1 over k times sine of kx plus c. Now, hopefully this helps in terms of u substitution really can help us out with this e to the kx, sine of kx, cosine of kx type problems where k is any non-zero number. I want to throw a few kind of words of caution. This does not work if we're looking at integrals like, say, e to the 5x squared. This x squared is giving us problems here. So this really only works for the problems in which we have some number times x to the first. So I'll say the u substitution only works for problems like this that have a number times x to the first power. Which I'll just say x to the first. So what that really means is, for example, if we have something that's like cosine of, say, 7x cubed. Or we have something like cosine of 7x. U substitution only works on the case on the right. U substitution will not work here. You can try it, but unfortunately, you're going to run into some roadblocks.